Okay, I hope we all have our screens display with time domain analysis. So today we are going to look at time domain analysis. And previously we saw in our earlier discussions that systems or plants which us as control engineers aim to control or to design, these systems are not static. In other words, they are dynamic. Their states evolve with respect to time. And of course, understandably, due to a number of factors. These factors may include external disturbances or perturbations, nature of the input signals, as we saw earlier in our last meeting. These all factors make the system dynamic, so it can't be static. So as we discussed in the previous meeting, you should be able to know that a system can never or rarely, practically, it can never be static. It will always be dynamic. So the manner in which a dynamic system responds to its input expressed as a function of time is what we call time response. The manner in which a dynamic system responds to its input expressed as a function of time. The theoretical evaluation of time response is undertaken in the time domain, and thus the name time domain analysis. There are other definitions here, which we shall see later, which we shall expose on later. But here, this bullet says to determine the time response of a system, we need to know the nature of the input or inputs expressed as a function of time. Secondly, the mathematical model of the system. So we looked at modeling in the previous meeting. Excuse me. Modeling as an equation or a representation of a physical system by an equation or a set of equations. So you remember modeling, I think. So we are at this bullet, the transient response. Let me first move a little bit to the next slide. So when you look at this curve, when you look at that graph, it is basically a constant velocity curve, which has position or displacement against time. You remember the constant velocity graphs, and we studied in physics, so Form 2. Yeah, so this curve generally describes a dynamic system where we have a transient period and a steady state period. So going back to these definitions, they are defining a transient response as the component of the response, as that component of the response that usually decays to zero as time increases. It is a function only of the system dynamics and is independent of the input quantity. Transient response. So this is This is the transient response, this curve here. So going back to the definition, I want us to understand this very well. They're saying transient response, this component of the response will, for a stable system, will, for a stable system, decay, usually exponentially. Exponentially, you know, it decays more and more rapidly or substantially in a very short period of time to zero as time increases. It is a function only of the system dynamics and is independent of the input quantity. You should be able to note that. And defining steady state response, this is transient response. Now, steady state response, this is the response of the system after the transient component has decayed and is a function of both system dynamics and the input quantity. So the steady state occurs after the transient period. So this is the transient period as clearly defined or shown on this graph, the transient period and the steady state period. The steady state period, you see it happens after a transient period. So basically here they are describing a system. X naught is the system output, in this case, represented by displacement or position. This is a position stroke displacement against time curve or graph, where we have a constant velocity, or this ramp, a ramp which is a ramp means a sloping surface. So we have other components, transient error and steady state error. They are defined. We can say on this page or this slide, the total response of the system is the sum of the transient and steady state components. So the total response of the system is the sum of all this, the transient period and steady state period responses.
Excuse
they
me.
make up. Yes.
First go back. Let's go back to the previous slide.
The previous slide.
What do you mean by system dynamics?
The system dynamics means the system itself. You know, for example, okay, last time I gave you a scenario that a control engineer like you, Robert, has been called upon to design a control system for an oil pipeline, some section of the oil pipeline. So you must analyze this system. So the system dynamics of that pipeline, what is it? The pipeline, for example, may be cylindrical. So if it is cylindrical, what material is it made of? Is it plastic? Is it metallic? If it's metallic, what kind of a metal is it? Is it cast iron? Is it, you know? So those are system dynamics. So those characteristics that define the system, its physical characteristics are what we call the system dynamics, the system itself, or the plant itself. Is it clear, or I've not explained it clearly?
It is okay.
Okay, so so we're here. So the total response of the system is the sum of the transient and the steady state components. So we've seen already that that this xi is our input. It is our input, the system, and this is our output from the system, or the response from the system. So it is clear stated here that x naught is the system response. So transient error. What is transient error? We've seen that this is the difference between the system input and its output during the transient period. That is the transient error. Clearly, this should be simpler to comprehend. During the transient period, the transient error is the difference between the input and the output during the transient period. Likewise, the steady state error is the difference between the two input and the output during the steady state period. Okay, these definitions must be clear to us now. So this at this point, a control systems engineer aims at designing a system or a plant with minimum errors. So we've already seen that taking an example of this system, we already have transient error, we already have steady state errors. So as a control engineer, you must make sure that these errors are reduced, because to get the optimum output of your system, to get the maximum efficiency out of your system, these errors must be reduced. We shall see in the subsequent meetings how we reduce these errors. Okay, so we are looking at we are generally looking at time domain analysis, and we've looked at a few definitions that we shall meet. At this point, we shall look at, or we shall talk about, Laplace transforms. This should be very familiar to us at this point. After spending 6 years doing this course so far, yeah, we should be able to understand or remember what Laplace transforms are. So we shall just, look at Laplace transforms briefly to make ourselves remember or to review, because going forward we shall use Laplace transforms in our equations. So to compute the time response of a dynamic system, it is required to solve the DEs, the differential equations. These can be system mathematical models for given inputs. There are a number of analytical and numerical techniques available to execute this. In our course, we shall use Laplace transforms. This method transforms the problem from the time domain to the Laplace domain. From the time domain to the Laplace domain or frequency domain, as we shall see later. It simplifies the complex time domain differential equations, DEs. DEs is differential equations, to S-domain algebraic equations. When the suitable solution is obtained, it is inverse transformed back to the time domain. So this figure shows the process that we go through. You have an equation or a differential equation in time domain. You do Laplace transform. It goes into SC domain or frequency domain. You obtain that equation. Then you can do inverse Laplace transform to take it back to a time domain equation or an equivalent of that time domain equation. So basically, this is what it means. You are aware of, I hope you are aware of this general Laplace transform equation. This Laplace transform, this is the sign to mean that we are going to do Laplace transform of a function of time, t. Then the general, how we define this general equation, it is an integral from 0 to infinity of this function. We are trying to do Laplace transform on a function of t, a function of t or a function of time, then e to negative st dt. Then you'll be able to change your equation, a differential equation from time domain into f domain or s domain. This is a general equation and we should take note of this. This is a review. I hope we've done this in engineering mathematics before. We are going to take a look at a simple example where you have a function of time equal to 1. In control systems engineering, we shall call this a unit step. Please note this because we shall meet it in the subsequent slides. It's called a unit step. So what do you do if they say find a Laplace transform of f of time equal to 1? No, we shall, from the knowledge of the general Laplace transform equation, we should be able to come to this conclusion that the Laplace transform of the unit step is 1 over s. How? I think it's not so hard. Our function of time is equal to 1. So from the general equation, we shall replace this ft with 1. Then e to the power or to st remains, then dt. So we are going to integrate from 0 to infinity this whole component. When we do the integration and we put in the limits, we are supposed to come to this. Is that okay? I beg to move forward. Example 2, following the same steps to find the Laplace transform of the function of time equaling to this e to at. A is a constant, remember, in this whole thing. So we shall be able to deduce that the Laplace transform of this component comes to 1 over s minus a. I think these are examples. Actually, I got them from engineering mathematics, Strode, that book of engineering mathematics. I hope you've seen this before, so we should not be spending too much time on this. Okay, example 3, the same thing. Here it was, in this example, it is a positive. Then here in this example, it is a negative. And you see what happens. The sign changes in the denominator. Okay, this is just a review from our engineering mathematics. Excuse me. So we are going to look at or to review the properties of Laplace transform. One of the properties is they are derivatives. The Laplace transform of a time derivative is given by this general equation where where f of 0, the derivative, then this is the first derivative of our function, initial conditions, or the values of f of t, and this is the derivative of our function. At initial equation, at initial condition, it means t is equal to 0. Then linearity, then constant multiplication. There are other properties which include initial value theorem, real-shift theorem, convolution integral. Yeah, all those are properties of Laplace transform. But for us, we shall look at the derivatives, where we shall be able to do Laplace transforms of first order, second order differential equations. These others, we shall not look at them really much. This is still a review. I just got this from the reference book, control engineering, advanced control engineering, and even advanced engineering mathematics. So when you have a time function as a unit impulse, when you do Laplace transform, what do you get? You get 1. A unit step, we looked at it, you get 1 over s. We looked at the first example we looked at here is a unit step, where you get 1 over s. If it is a unit ramp, get 1 over s squared. If it is, I'm sorry, this is not really much clear. If it is t to the power n, standing for any number, this is how you go about it, and so on and so forth. Here in this slide, we are talking about inverse Laplace transform of the function of s being given by this general form of the equation. So in practice, inverse transformation is most easily achieved by using partial fractions to break down solutions into standard components and then use Laplace transform pairs. These are the Laplace transform pairs they are talking about. Really, this is a review of what we studied in engineering mathematics. Okay, this is also a review of common partial fractions, factored roots. This is how it is represented. Repeated roots. This is how it is represented. Second order roots. This is how they are represented. So this is a review. I should remind you. Okay, now let's go to transfer functions. We defined the transfer function, I think, in our first meeting or second meeting. We defined the transfer function, but we can still redefine it in a sense of Laplace transforms. It can as well be defined as the Laplace transform of a differential equation with 0 initial conditions. It is a very easy way to transform from the time to the S domain, and a powerful tool for the control engineer. So I think it was in the previous meeting, one of the members asked about the significance or the rationale of transfer functions. Why do we, why are we deducing or finding these transfer functions from our block diagrams of the block diagrams of the control systems? So it is clearly stated here that it is a very easy way to transform from time domain to S domain and a powerful tool for the control engineer, as we shall see shortly. Okay, we have an example here. We have an example, sorry about that. We have an example that find the Laplace transform of the following differential equation given. Oh, I'm sorry about this interruption in network. Okay, find the Laplace transform of the following differential equation given initial conditions x not equaling to 4 and this equaling to 3. Then assuming Roman 2, assuming zero initial conditions. So this is our differential equation. This is our differential equation. I want to confirm that we are all on, and because I see my network is not stable. Can all of you get me, or I'm just talking to myself?
So we are getting you.
All right.
We are getting you.
All right. Okay. So this is the differential equation.
Excuse me, sir.
Yes, please.
The previous reminders to Laplace transform, are they very, very necessary in terms of exams being examinable? Are they examinable, or they are just for the purposes of making us remember?
Yeah, it is just making you remember, because I'm not going to ask you about Laplace transforms, going into deep, but or however, you should note that some of the equations we shall have here shall use Laplace transforms, though not into the deep sense of Laplace transforms. We can use the table here. We can always refer to the table here. If we have a unit step, what is its Laplace transform? To be 1 over s. If it is a unit impulse, it is 1. So we are not really going deep into Laplace transform, but this is just a reminder, and this is just a review.
Another thing, so this table is always given in the exam.
No. This table is not given. This table just shows, coming to 1, if it's a unit impulse, if its Laplace transform coming to 1, there are steps. It doesn't just, jump to be 1 or to become 1. So there are steps. So you should be able to know those steps, but I'm not going to ask you about those steps.
Excuse me, sir.
Yes, Robert.
I'm on the issue of, because you see, someone might not be, okay, they might be able or might not be able to cram the whole of this table. So, and even in engineering math, they used to give us, provide with us the table containing the transforms. So that when you meet it, you just go there and apply that without going through all the other, because the calculation will be too long.
Well, I understand your worry. I understand your worry, Robert, but please worry not. What I'm going to ask, or what we shall meet, or what we shall be using in this control systems engineering, we are using a unit impulse, we are using a unit step, we are using a unit ramp. Yes, we are using a unit ramp in our calculations. I don't think we are going to look at these other ones. So surely this should be able, these are really simple to be remembered. Not so.
Okay.
All right. So we are really going to, to focus on unit, because our question will ask considering a unit impulse. So directly, you should be able to remember that the Laplace transform of a unit impulse is 1. Should be able to remember that the Laplace transform of a unit step is 1 over s. And you should be able to remember that the Laplace transform of a unit ramp is 1 over s squared. We are not looking at all these other ones. It was just a reminder. Okay, let's go back to our example. We are required to find the Laplace transform of the following differential equation, given 1 initial conditions as this, and given 2 0 initial conditions. Okay, this is the differential equation we are looking at and which we need to do to perform the Laplace transform on. Okay, let's look at the solution. Excuse me. Okay, considering initial conditions of x not equal to 4 and the first derivative with respect to t equal to 3, we shall refer to this equation, which is a characteristic of Laplace transforms, or a property of Laplace transforms. You remember we looked at this derivative in the characteristics or properties of Laplace transforms. We have this equation, and we are going to refer to this particular equation if it is a derivative, just like we have in this case. So we are referring to that property. Then it is stated here. Our differential equation is this. Okay, so let's focus on this. If I can increase a little bit on the font. Okay, now here the trick is, if it is the trick, how we are going to handle this problem, we are handling term by term. Term, I mean, this is one term, second one, third one, and maybe a fourth one. But we are handling this, and we apply our characteristic equation, or we apply our property of a derivative. So this is it in this first bracket. When we apply this property in here, this is the second derivative, and you should note, and please note that while you're using this property, if you're applying it in a second derivative, if a function is a second derivative, you apply all these terms, this first term, second term, and the third term. You apply all of them, as you shall see. And if it is a first derivative, as in this case, we apply this term and this term. And if it is a case without a derivative, it's just a function, we only apply this term of the property. Okay, let's go. Okay, if we apply this, remember I said if it's a second derivative, we are going to apply the whole of it. Let's go. Now, if we apply this in this, we shall have s squared. Why s squared? Because we are saying that it is s to the power n, and in this case, n is any number representing the number of the derivative, and here it is 2. So that's why it becomes, here it is the second derivative, and that's why it becomes s squared, right? Then this is the general form, but if we are to relate it to our differential equation, fs will be the, okay, f of t will be x naught of t. So when you do Laplace transform, it becomes, you know, this is in lowercase. When you do Laplace transform, it goes into uppercase, right? Likewise, this is lowercase of our function x naught. When we do Laplace transform, it becomes x naught of s, but x is in uppercase. Please note that. So that's why it becomes x squared x naught of s. We have done Laplace transform after putting this, you know, after considering this general form of a derivative, general form of Laplace transform of a derivative. So we get this. Remember, we said for a second derivative, we apply all these three terms. So it will be, after applying this, we get this, not so? So we continue, say minus our function, f, our function, in our case, it is, sorry, we apply this now. Let's see how it goes. To be minus, first, s to the power n minus 1. In this case, what is n? N will be 2 because it is the second derivative. So it will be 2 minus 1, which makes it 1. So it becomes s to the power 1, and any number to the power of 1 remains that number. I think from our primary or junior school mathematics. So that's why we shall have our s appearing here. But why do we have a 4? We have a 4 because this is our function f of naught represented by x of naught, which is 4. So it will be minus 4s. Then we continue and apply this. When we go to this, it will be s to the power n minus 2. In our case, n is 2. Then to be 2 minus 2, which is 0, and s power 0 will be 1. Any number to the power 0 is 1, right? So it will be 1. Then this is a first derivative of but in this case we are taking the initial conditions of the first derivative equaling to 3. So remember, we had already gotten 1 from this expression, and now it will be 1 times the 3, so it will be minus 3. So we have successfully applied this property in this term. So we go and say plus 3 into plus this 3 into this. Now we are going again apply this into this first derivative or into this term of our differential equation. So we said if it's a first derivative, we consider this term and this term. We consider two terms. So it will be 3 into, okay, let's put this into this. In our case, n will be 1 because it's the first derivative, so it will be n. To be n equaling to 1, so it will be s to the power 1, which will be s. That's why we have s here. And this is the Laplace transform of our function, f of s. And in our case, it will be x naught of s, and x naught, please note, it will be in upper case. So that's why it is x naught, meaning it has been Laplace transformed. Okay, we continue. Remember, we have finished applying this, and we are also going to apply this into this. So it will be f of naught, which is x of naught, given as 4, to be minus 4. And this term will be s to the power 1 minus 1. Already we have 1. We already have n equaling to 1 because it is a first derivative. So it will be n minus 1, which will be 1 minus 1, sorry, which becomes 0. Then it becomes s to the power 0. Any number to the power 0 becomes 1. So that's why we shall remain with a 4. So we have successfully applied this property into this part of our differential equation. So we continue, plus 2. Remember, we said if in that part of the differential equation there is no derivative, it's just a function, we only apply this part of the property. So when we apply this, s definitely is 0 because we do not have a derivative. So it becomes s to the power 0, it becomes 1. So it will be 1. Then this function, or this part, it will be, it's clearly a Laplace transform of our function, which will be x naught of s. Then we have as well successfully applied our property in this component of a differential equation. Now we go to 5. When you go to 5, when you do Laplace transform of a constant or of a number, what do you get? So that's why Robert and other of the class members, you should be able to know that a unit step, if it is a unit step or if it is a constant, as 1, it can be 1, it can be 4, it can be 10. In our case, we are having 5. If you do Laplace transform of that constant, it becomes 1 over s. Okay, it is that number 1 times 1 over s, right? So if it is 1, it becomes 1 over s. If it is 10, it becomes 10 over s. So this is exactly what we have here. Since it is a 5, it will be, when you do Laplace transform of a 5, it becomes 5 over s. I think Robert now and the rest of the members, you can now comprehend why we had to review this table. Robert, are we fine?
Yes.
All right, okay. Let's continue. I think up to this point, we are all on the same page. Then after getting this, surely you should be able to rearrange and come to this equation. Then you do further rearrangement and get this. Then finally you get x naught of s equaling to 4s squared plus 15s plus 5 over the whole of this. So when you do the rearrangement, you come to this point. But the whole point, you should be able to understand how you apply this property of Laplace transform of a derivative into your second order. This is a second order differential equation. We reviewed differential equations in the previous lecture. Okay, this was Roman 1 applying initial conditions as this. So we shall go to Roman 2, where we are required to apply or to use initial conditions of x not equaling to 0 and our first derivative equaling to 0. These conditions are called zero initial conditions, where you have your function equaling to 0, sorry, and its first derivative as well equaling to 0. Let's go again. This is our differential equation, and remembering that we shall apply this property of Laplace transform into our differential equation. If it's a second derivative, we apply this, and this into this. If it's a first derivative, we apply this and this. If it's a function without a derivative, we apply this first term of our property. So going through the same steps we went through in the previous example, we should be able to come to this point. Okay, let's see. If we apply the whole of this into this term, we shall see that it will be s to the power 2, which is s squared, and which is here. Then, of course, the Laplace transform of our function x naught, which becomes x naught of s, x naught in uppercase. Then plus wait, before a plus, we said if it's a second derivative, we apply this term, and this term. So if we apply these terms and this term, if we apply these terms, this one and this, it gives us 0. That's why we have x squared, x naught. Okay, but let's see. If we apply this, what happens? In this term, we have, but it is clear because this term is multiplied by our function f naught. In our case, it is x naught, and x naught is 0. So when you multiply 0 in this term, definitely it becomes 0. Likewise, this term also is multiplied by the first derivative, but the first derivative, as the question states, is given by 0. So if you multiply 0 in this term, it will be a 0. So we remain with x squared, x naught, after applying this whole property in this term. So plus, okay, well, plus 3, then times, times what you get after applying this property in this first derivative. We said the first derivative.
Excuse me.
Yes, please.
Hello?
Yes, please.
What is the difference between that capital F of S and that small f of naught?
Small f of naught is a function. Then capital S is the first. Capital S Capital F is the Laplace transform of that function.
Okay.
Okay, so
Excuse me.
yes, please.
I'm asking about the n.
Hmm.
Is the n the same for the whole expression, or it keeps on changing?
The n changes accordingly because, for example, when we applied this property in this term, our n was 2. But when we apply this property in this term, our n becomes 1 because this is the first derivative, this is the second derivative.
Okay, thank you.
Okay, so let's finish this off. I think at this point, after we had reached at this point, clearly in initial, when we have 0 initial conditions, these terms diminish or disappear. This term and this term, they disappear. We only apply this term in all the 3 terms of a differential equation. So you'll be able to come out. Again, you do a Laplace transform of 5, which will be 5 times 1 over s, which becomes 5 over s. So you do rearrangement and you come to this equation, and we have called this one equation 1. Moving forward, so first, this bird says the example in 2 above is easily solved using transfer functions. So again, if I can emphasize on a point, because one of the members asked from the previous lecture that what is the rationale or what is the significance of us finding these transfer functions. You've clearly seen in these examples how we've used the transfer function to solve a differential equation, a second order differential equation. And this is a very, very important tool that we shall be using in control engineering, even when we come to a process of understanding how to design a controller, because you must go step by step, understanding an equation, understanding a system or a plant, understanding its characteristics, modeling your system. Modeling, we said it is an equation representation of the physical characteristics of your system or your plant. So after modeling, you come to transfer functions. Then a transfer function, you do a Laplace transform to come, to a point where the controller you're going to design understands what you're trying to do. All these steps, all these activities are aimed at going to designing a controller for a control system, as we shall see later on, I think in the next meeting. So we've seen that the example above has been solved using transfer functions, especially here. And the figure A below shows the general approach. The general approach is shown in this figure, where you have x of I. This is your input and this is your output, and this is the transfer function. They are defined here. Xi of s is the Laplace transform of the input function. X naught is the Laplace transform of the output function or the system response, and g of s is the Laplace is the transfer function or Laplace transform of the differential equation. So the differential equation we had can be transformed into this block diagram, and we can define, generally, we can define this block diagram using this equation 2, where x naught of s, which is x naught of s, is the Laplace transform of our system response or output of our system, equal to the transfer function times its input. This surely is clear, and in figure B, let's see, let's continue. We can define a general second order transfer function as in figure C. In this figure, we are defining the general second order transfer function. The general second order transfer function given by this equation, where you have a second derivative of our function with respect to t, plus b, the first derivative of our function with respect to t, plus c, x naught. Please note that a, b, c, all of those are constants. Constants, they can be 1, 2, 3, 4, up to 9. Can be 10, can be 11, can be 20. So a, b, and c are constants, and x naught is our function, equaling to k of times xi. Xi is our input function, and k is also a constant. So it can be generally be written, okay, it can be simplified as this: x squared representing the second derivative of our function with respect to time, and s here representing the first derivative with respect to time. Yeah, so this should be clear. This equation can as well be rearranged as follows. When it is rearranged as this, you have the output function or the system response on this side. You have this whole function multiplied to the system input, gives you this equation, and this equation can be represented by a block diagram as it is shown in figure C. So this is clear still. Comparing equations 2 and 3, where is equation 2? And this is our equation 2, which is a general which is a general equation of the approach of the transfer functions. This is a general equation, and it is equation 2. So in this bit, we are saying comparing equations 2 and 3, the transfer function g of s, the transfer function g of s becomes this. Yeah, this is clear. If you see, if you look at this equation, x of naught equaling to this, and you compare it with this, you realize that our transfer function in this, when you compare the two equations, is this part where k, where we have k over a s squared plus bs plus c. That is the transfer function, and it can be represented in form of a block diagram as in figure C. Yeah, surely I hope these are very, very simple things, and I told you control engineering is not really hard. We shall try to make it as simple as we can, because we want us to be very, very practical. This marks the end of our simple discussion today. I hope there are not any questions. If there are any questions, let's have them, and we have this closed, and we'll meet another day. Do we have any questions?
Slide number 14.
Slide.
Number 14.
Slide 14. What about what's up? What about that slide? Yes.
Yeah, we see we have the x not s at the end. Which is that of 4s squared plus 15, like that, like that. So when you go to the next slide, maybe I didn't get you clearly. Go to the next slide. Oh, okay. I have seen where it is. All right.
Okay. Are there any other questions?
Maybe guiding questions for, we would like to have guiding questions.
Oh, yeah.
Because you only gave guiding questions in the first lecture.
And the second one, I think. Yes. And
yes.
Yeah, the guiding questions will come, but today's discussion surely has been a simple one. The question can come, in a similar manner that find the Laplace transform in the following differential equations, and the differential equations can this can change. The digits can change, but it's the same approach. This is really simple, not so. All right, I beg to conclude this meeting at this point. Thank you very much.
Welcome.